Hello, chemistry. Today we are going to go over an introduction to mole ratios and molar stoichiometry. And stoichiometry is defined simply as applying mathematics to chemical equations. Basically, if you have X amount of one substance, how much of another one do you need, or how much of another one you can get? It is kind of a term that relates to the fundamental mathematics of chemical reactions. So it begins with the chemical equation, which we've seen before. And as we've seen before, my app here um, does not like the arrow that is in Microsoft Word. So I'm going to go ahead and draw in my own arrow in a nice color here. There we go. So this reaction we've seen before. This is the reaction of ethane with oxygen in a combustion that produces carbon dioxide and water. We've talked a little bit about these molar coefficients, in this case 2, 7, 4, and 6, which serve to balance the equation. So the chemical formula of ethane is dictated by the electron structure, and oxygen is a diatomic molecule for Han F. Brickel, and carbon dioxide and water, both are common substances that we know. So you cannot balance an equation by changing subscripts. That would be changing the ingredients. So instead we add these molar coefficients. And the extra layer that we use the coefficients for is to talk about relative amounts of substances. So at the molecular level, for every 2 molecules of ethane that you have, you're going to need 7 molecules of oxygen gas in order for it to react. You could also say, if you want to bring in Avogadro's number, 6 times 10 to the 23rd particles, that whenever you have 2 of that number of particles, you'll need 7 times a mole, so 7 times 6 times 10 to the 23rd particles of oxygen to react with it, and then you would produce 4 times 6 times 10 to the 23rd particles of carbon dioxide out of it. So whether it's particle to particle or mole to mole or anything in between, these molar coefficients represent a ratio of amounts of particles. And that is important, that when we talk about these, we're talking about numbers of particles. And the problem here is that number of particles is not something we can really directly measure. We can measure mass, we can measure volume, we can measure all sorts of things, but we can't directly measure particles. So we'll get to how we make that conversion in a moment, but it's an important skill to be able to look at an equation and identify the mole ratio. So if I said, like we've been talking about, what is the ratio of ethane to oxygen in terms of moles, you could say that it's 2 moles of ethane to 7 moles of oxygen. The colon notation is one way to express a ratio. The other way that you can express a ratio is as a fraction. So you can say 2 moles of ethane to 7 moles of oxygen, or you could say 7 moles of oxygen to 2 moles of ethane. You can express it either way. These 2 expressions of the mole ratio as fractions are the preferred ways to think about mole ratios, because these become a tool, literally a tool to convert from one substance to another. If I know how much ethane I have, I can use the mole ratio to find out how much oxygen that I need. If I know how much ethane I have, which that should be 2 moles, then I know how much carbon dioxide I will produce. And notice here, this is a fraction that can be simplified. We can reduce this to be 1 to 2 if we want. That's usually good form. But not only can I say, well, if I have 2 moles of ethane, I can produce 4 moles of carbon dioxide, but I can also say that if I have 4 mole, or if I want 4 moles of carbon dioxide, did it again. If I want 4 moles of carbon dioxide, then how many moles of ethane would I need? I need 2 moles of ethane to produce that. So just like when we talked about describing a chemical reaction, converting that into a sentence in English, you could say the reactants produce the products. In a mole ratio, you can also compare the products back to the reactants, and it really depends on what your situation is, which method you want to use. But I can say it's a 2:7 ratio of ethane to oxygen. It's a 7:4 ratio of oxygen to carbon dioxide. It's a 7:6 ratio of oxygen to water. There's all sorts of combinations that you can get out of this. So the first step then to convert an unmeasurable quantity in number of atoms or molecules into a measurable quantity is molar mass. And so molar mass is the grams per mole. So the mass in grams for each mole of a substance. That's the standard unit of molar mass. And molar mass really comes off of the periodic table. So if we zoom in the periodic table, we can see what we have in the past called atomic weights or atomic masses. And those all represent the mass, the molar mass of any of the elements in grams per mole. So right here we have iron. If you have 55.85 grams of iron, you have 1 mole of iron. If you have 98.91 grams of technetium, you have 1 mole of technetium. So that's important to recognize that every element, even when we have exactly the same number of atoms, each element is going to have a different mass. And this is why we cannot compare the mass of one element to the mass of another. That 1 mole of phosphorus, for example, is going to be less than half the mass of 1 mole of arsenic. If our reactions occur particle to particle, we have to know the number of particles, or we have to know the number of moles, and that has to be calculated from the molar mass of the elements involved. So if we take a look at these examples that we have here, it went around to the other side, so let me fix this here. So this is NH4 to SO4 over here. We'll kind of cross that out. The way that you determine a molar mass is pretty simple. Add up the masses of all the atoms that make up the substance. So for an element, if you need a mole of iron, just take it straight off the periodic table. But we have sodium hydroxide here. What's the molar mass of that? Well, it's going to be the sum of the molar masses of the different elements. If I look at the periodic table that we used up here, it says that the molar mass of sodium is 22.99 grams per mole. The molar mass of oxygen is 16.00, and the molar mass of hydrogen is 1.01. If I add all of those up, then the molar mass of sodium hydroxide works out to be 40.00 grams per mole. 6 times 10 to the 23rd particles of sodium hydroxide will have a mass of 40 grams, almost exactly. Sodium hydroxide is one of those fun substances where to a few decimal places, the molar mass works out to be a nice even number. Magnesium hydroxide, though, we have a different subscript because magnesium is a member of a different family of the periodic table, so a different oxidation state. For magnesium hydroxide, I need a magnesium, 24.31. I need, whoops, zoomed in a little bit there, grams per mole. I need 2 oxygens because this 2 distributes to each element inside the parentheses. So this is 2 hydroxide groups. So I need 2 times oxygens molar mass, and I need 2 times hydrogens molar mass. And when I add all of those up, I get 58.32 grams per mole. So magnesium hydroxide, as we would expect, is heavier than sodium hydroxide, not by a lot, but by a bit. And then ammonium sulfate, if we add all of this up, I'm going to need 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens. And if you add up the molar masses of all those elements, you end up at 132.14 grams per mole. So this is one skill that you need to have of being able to, with a periodic table, determine the molar mass of a substance. That is a key starting point for doing stoichiometry with chemical equations. What this would allow us to do now is if we go back to this equation to say, all right, if I have so many grams of ethane, how many grams of water would be produced? Well, it's going to be based on the number of moles of ethane that represents times the mole ratio times the molar mass of water would give us the mass of the product. All of these things are going to use basic algebra skills when we ultimately get to it, but we'll kind of build one step at a time working through this, and molar mass is the first step. For gaseous reactants and products, if we want to work, because it's very difficult to measure mass of a gas because you run into buoyancy issues and things like that. Usually we measure volume of a gas at a certain pressure. And so standard temperature and pressure is 1 atmosphere of pressure. And usually we say 273 Kelvin. Kelvin being the most standard of the temperature scales, the absolute temperature scale that starts at 0, absolute 0, and goes up. This is equivalent to 0 degrees Celsius and 32 degrees Fahrenheit. But most equations in chemistry require the use of Kelvin, mainly because in a lot of the mathematics, you need to make sure that your quantity doesn't have any negative numbers, and Kelvin temperatures cannot be negative. So standard temperature and pressure, 1 atmosphere, 273 Kelvin. And 1 mole of any gas at standard temperature and pressure is going to have a volume of 22.4. I wrote this as backwards. 22.4 liters per mole. So 22.4 liters represents 1 mole of a gas at standard temperature and pressure. If you squeeze it, you compress it, you heat it up, you cool it down, then the volume is going to vary. That's part of the reason why gases were so much more different than solids and liquids, is because they are compressible. But at standard temperature and pressure, if you have 1 mole of a gas, it'll measure 22.4 liters. And I'll show you what this looks like in class another time. But just if you're curious, the origins of this, there's an equation that we may or may not get to work with this year with the hybrid thing, but it's called the ideal gas law. PV equals nRT, or PIV-NERT, as I usually call it. It's pressure times volume equals the number of moles times temperature times one of the fundamental constants of the universe, the ideal gas constant. And if you plug in standard temperature and pressure to this equation, you get 1 atmosphere times the volume equals 1 mole times R, which is 0.0821 liters dot atmospheres over mole dot Kelvin. Real kind of complicated little unit that balances everything out. So 1 atmosphere times the volume equals 1 mole times the ideal gas constant times 273 Kelvin. And you're going to solve by dividing both sides by 1 atmosphere, divide both sides by 1 atmosphere. And so 1 cancels, moles cancel, atmospheres cancels, Kelvin cancels, leaves you at liters. And if you multiply 0.0821 times 273, you will find out that that equals 22.4. This equation is what you have to use if you ever have a gas that's not at standard temperature and pressure, but usually in introductory chemistry, we focus on working just with things at standard conditions, because then we could use this kind of shortcut number, 22.4 liters per mole, of a gas. So let's do just a couple example mass to moles, molar mass kind of calculations. We'll work through these a little bit more together in person, but just to kind of show you where this math goes. Let's take, for example, our magnesium hydroxide. Whoop. Magnesium hydroxide, which we had before, and if I say I have 37 grams of magnesium hydroxide, how many moles is that? And we determined that magnesium hydroxide has a molar mass of 58.32 grams in 1 mole, or we can also say, because really this is a ratio, grams to moles, that 1 mole of magnesium hydroxide has a mass of 58.32 grams. When it comes to conversion factors, you can use the fraction or its reciprocal, whatever works to solve your problem. So if I have 37 grams and I want to multiply that times some conversion factor to get to number of moles, then what we want to do is have grams on the bottom to cancel out this other grams. So I'm going to take this conversion factor here and plug it in. 1 mole over 58.32 grams. And so 37 divided by 58.32 is 0.63 moles. Does that make sense? Well, if 1 mole is 58 grams and I have 37 grams, then that should be definitely less than 1 gram, but more, or less than 1 mole, but more than half a mole. So that makes sense. Mentally, the thought process here is proportions. Where if I have, I have grams over moles equals, say this is, 1 gram over 1 mole, and I've got 37 grams over X. You would do the cross multiply and divide. Really, this equation, as you see it here, is the cross multiply and dividing thing already being done, being completed. And I will say that from my perspective, get rid of the cross multiply and divide thing. It is great for the simplest of problems, but honestly, we're going to be doing some multi-step calculations here. And although it's helpful to mentally remember that this is a proportion, don't set it up quite the same. Set it up as a string of multiplied fractions, what's called dimensional analysis or the factor label method, because this becomes much more useful when there's 2 or 3 steps that you need to do. Say you have a unit conversion, your mass was in kilograms, you need to convert it to grams and then multiply it by the molar mass. This method's a lot better. So let's say that I have 4 moles of sodium hydroxide, and I want to know what the mass of that is. Well, similarly, I have 4 moles of NaOH, and I have that molar mass 40 grams per mole. In this case, I do want moles on the bottom, so that's 40 grams in 1 mole. I do the math, that's 160 grams of NaOH for 4 moles. Notice on all of these for significant figures, I'm trying to follow those rules that we studied. Here's my measurement with 2 significant figures. Here's my answer with 2 significant figures. This one I probably could say 4.0 moles, 4.0 moles, and that gives me 2 significant figures there. But again, just try to keep your answers in the same realm of precision as your measured values were when you complete your calculations. A mass calculation. Here's an example going back to our original equation. What if I have 750 grams of ethane and I allow that to undergo combustion? How many grams of CO2 will be produced? So I start with my known quantity, 750 grams of ethane, and it's good to get in the habit of actually writing the formulas of the substances in, and I'll show you why here in a minute. Multiply by the molar mass, 1 mole over 32.08 grams, 2 carbons plus 8 hydrogens. And so notice that I put the grams on the bottom because I want grams to cancel out. So now I know how many moles of ethane I have, but I need to jump from moles of ethane to moles of carbon dioxide. So I go to the equation in the mole ratio, and that was 4 moles of carbon dioxide to 2 moles of ethane. So notice what happens here, that moles cancels out and ethane cancels out, leaving me now at moles of carbon dioxide. I then have carbon dioxide's molar mass, 44.01 grams in 1 mole. And if I do all of that math, I find out that I am going to produce 206 grams carbon dioxide when I combust 750 grams of, no, did I do 750 or 75? I think I did 75. I did the math. 206 grams of carbon dioxide, because that makes sense because carbon dioxide is heavier than ethane, and you also have twice as much of it. So I have an answer that's a little bit more than twice as much of the original substance I had, ethane. So caught myself there. I've got scribbles on my notes paper that I'm working with here, and sometimes even I can't read them. But so 75 grams of ethane will produce 206 grams of carbon dioxide after combustion. A quick example of a gas calculation. So for our 206 grams of carbon dioxide, I say, well, what's the volume of that going to be at standard temperature and pressure? Well, I first need to know how many moles that I have, because my conversion factor is 22.4 liters in 1 mole. So the molar mass of carbon dioxide is another one of these ones that's almost exactly on a round number, 44.01 grams. So that's going to get me moles of carbon dioxide, and then I throw in my 22.4 liters in 1 mole. So 206 divided by 44.01 times 22.4 is 105 liters of carbon dioxide produced from the reaction that we just talked about right here, 75 grams of ethane. So I know this all flew by pretty quick. We'll take this one step at a time, working through it. Your first task is going to be to show that you can do some molar mass calculations. We started with balancing equations. Well, really, we started with writing formulas. You have to write the formula correctly first. Then you have to balance the equation correctly. Then you have to have the correct molar masses. And once you have all of that, then you can start doing practical calculations that are important for inputs and outputs